Hello, everyone. This movie is presenting my final course project on Coursera called Machine Learning Foundations for Product Managers. The given task implies building a model to predict the electrical energy output of combined cycle power plant. This type of power plants looks like this. We have four variables of features: temperature, ambient pressure, relative humidity, exhaust vacuum, and the target value, net hourly electrical energy output. This. We have to validate at least two different models, which may be different algorithms, the same algorithm with different combinations of features or different hyperparameters and so on. Eventually, we need to choose the best model and make final prediction. Okay, let's look at what we have done. The data set looks like this. We have more than 9,000 rows. There are not missing values. The correlation matrix and principal component analysis show that all four features are important. We will try to use linear regression as the baseline, and then we compare this with other regression models. Linear regression is, as other regression models, is a model which estimates the relationship between target value and observed or input variables. This model calculates weighted sum of input values plus some free term to predict the target value. We can write it in vectorized form. The point is that we consistently multiply the row vectors with the input variables by the column vector with coefficients, like it's depicted in the image. Our goal is to select such theta values so that the prediction error is minimal. That's why we need to choose a loss function to minimize. We use mean square error. Of course, it's not only loss function, but one of the most used. In the case of linear regression, the theta coefficients can be calculated analytically, like this. We don't need to use gradient descent in this case. In short, we just need to multiply some matrices properly. Okay, we split data on train and test set in proportion 80 by 20. Our data has different dimensions, hundreds, tens. We need to bring them to the same scale. After multiplying matrices, we got thetas, we got our coefficients, which we can use for prediction. Let's calculate our predictions. This, it seems to be true. Mean square error is equal 20.16. Not so bad. If we check this result using out-of-the-box Cologne algorithm, we get the same result. Okay, to compare different models, we use a so-called k-fold approach, which implies that we cut some part of data off to use it later as a test set. The remaining data will be used for training and validation, like it's pictured in this image. The next model we can consider is polynomial regression. It's like a tree which creates new features from existing ones. We have only 4 features, so in accordance with that formula, we will get 15 features on which we can train the aforementioned linear regression. So we try to approximate data distributes non-linearly. We split data on 3 folds. We can see that that indexes of rows don't overlap each other. We launch 3 iterations on different subsets, and then we average the result. So we got the predictions with less error, about 17.89 instead of 20.16. Okay, let's consider regression models with regularization. Regularization is a imposition of certain restrictions on the model in order to avoid overfitting. It's used to limit the size of coefficients of the model. To do that, we implement so-called regularization term. It means some penalty which we exert on the model to keep it relatively simple to avoid overfitting. Okay, the first type we consider is rich regression. Its loss function looks like this. What alpha means? Alpha is a normalization parameter which determines how much we regularize the model. At alpha equals 0, the rich regression becomes just a linear regression. With alpha close to 1, the best possible coefficients tend to 0. We will use alpha is equal 0.2. As usual, we launch 3 iterations, then we get the average result, 21.21, instead of 20.16. Okay, the next type is lasso regression. It uses a slightly different regularization term. This. Okay, launch the calculations. And unfortunately, the results are much worse than other models have showed. Okay, we have a winner, polynomial regression. Let's check our model, which was trained on 80% of data. Let's check it on test data. 3 iterations. And the result, we have MCA equal 17.39. The error on the test data is even less than on the training data. We can see all the result in the table. To sum up, we can say that the best model we consider it is polynomial regression, the best model for our data. Regularized models may perform worse if a number of the features is small and all the features are important. The order in which we perform scaling before or after creating synthetic features is of great importance. Additionally, I checked how the results change without scaling. I figured out that the results are almost the same, but I would recommend to do scaling anyway. That's it. Thank you for your attention. Goodbye.